We already looked at this last time, so just to repeat the definition, a suffix array is just the starting indices of all the suffixes once you sort the suffixes in lexicographic order. And one way to get that was using the suffix tree. If you take every node and order the child edges alphabetically by the characters, and we know there's only one edge for each character, so that's easy to do. If you do that for all the nodes, then in left to right order, or here top down for the leaves, you get the suffixes in sorted order. And it's convenient to assume here and throughout that this dollar symbol, the end of word marker, is smaller than all the real characters. Then you get this sequence of numbers, and that's the suffix array. And I hope I could convince you on Monday that some things may be lost if we forget the entire tree topology on top. But some other things are not lost. At least we can still find exact matches in the text of a pattern with two binary searches. And the runtime for that is no longer completely independent of n, the size of the text. But it depends on log n only, which is, for all practical purposes, almost as good. In this universe, everything's finite, so log n is finite. That's an empty statement. But log of the number of atoms in the universe is probably still 300. That's a sizable number, but a manageable number compared to all the atoms in the universe. Okay, let's see if you follow on this one. So last chance to vote on the attendance code. And then it's time for the suffix array. So I'm waiting for it for 29-ish, maybe 25 answers on this at least. Similar question as we had for the suffix tree, but now the suffix array, it's just about hammering in the definitions. I'll leave you a moment of peace for answering. All right, we have our 25. Hello. Okay. As always, this room. It will eventually show you. Now it's reloading. Let me do it here. Okay, so you can see the right answers now. Again, resist the urge to move around too much. Let's go through this briefly so that we're on the same page. So this is about the suffix array and the suffix tree and their relation. They're both built on a text t, which has n characters. And remember, we always assume for a suffix tree that we append the $sign. And I'm assuming that the alphabet symbol, the alphabet size is constant. Then L essentially lists the contents of the leaves in left to right order. That's if we draw the tree in the normal computer science way, root at the top and left is the smallest edge, smallest child edge, and so on, all the way to the right. If you keep doing that and then go left to right through all the leaves, you find the suffixes in sorted order. And so it's the indices of the starting indices of these suffixes, and those are stored in the suffix array. Now let's decipher what this one is. It's the text starting at the rth entry in L. So it's the suffix in that position. And what is that? It's a path label from the root to some leaf in the suffix tree for sure, because it's a trie of all the suffixes, right? And it's, if we take A together with this, it must go to the rth leaf, or the leaf of index r. Remember, we start with 0. But it's not necessarily the leaf that stores the number r. It's the inverse permutation. Another way to say the same thing, if you take the suffix of the text that starts at this position, we have this shorthand notation for that, then the fact that this is the index r in the suffix array says that's the rth smallest suffix of t. Let me do this one first. L and the text together are enough to solve the text indexing problem. That's what I've just shown you with the binary searches. Now the tricky one may be E. And here the important bit is, in terms of big theta classes, for a constant size alphabet, also suffix trees are linear space. They're theta of n space. But theta hides a constant factor, and that constant factor is much larger for the suffix tree than for the suffix array, where it's really one number for each leaf, or one number for each position in the text. So in a way, we shouldn't be too ambitious. The suffix array is still linear space, as was the suffix array, but the constants matter. All right. How can we compute the suffix array? An easy option is we take the suffix tree, which we know there's this magic black box that somehow constructs the suffix tree, so we might just use that. And we could do a traversal. So you start at the root and you do a depth first traversal. Whenever you reach a leaf, you will actually visit those in left to right order if you follow the alphabetic order in each node. And that would give you the suffix array. However, it kind of defeats the point of having this sleeker data structure if we first have to build the fat suffix tree to get to the suffix array. And just by the definition of the suffix array, it's now much more transparent what we have to do if we build this from scratch. All that we need is all the suffixes of the text in sorted order. And sorting is something we know how to do. So it's trivial to code by if you just do it that way, create an array of all the suffixes and pass it to your favorite sorting algorithm. That's trivial to code, because a sorting algorithm will be implemented wherever you code it. But that alone will not be fast. There's several problems with this. If you do it the naive way, then the array of suffixes would be an array of strings, each as a copy of the suffix. So that already uses quadratic space, not that great. Now you could be slightly smarter by noticing if you store the text once, you can sort indices, starting indices of suffixes, instead of copying out the strings. That would avoid the space problem, but you still have to do the comparisons. So whenever you ask the sorting algorithm to compare two things, to sort them, it would have to go all the way through the two suffixes until it finds a distinguishing character. And that, in the worst case, think again of our degenerate text where everything is just an A. That's often the worst case in this. For such a text, the comparison between any two suffixes takes as long as the shorter suffix is long. And so that sorting would give you n squared log n time. So that's way too slow to be interesting. But that's very pessimistic. I will say that most of the time you will not see this quadratic behavior. It only happens if the text is sufficiently self-similar. So for standard types of inputs, what was the standard type of input? For many types of inputs, it wouldn't be that bad. And so it's a first start. Maybe it's good enough for some. Depending on the application, it might be good enough. Now, if you know this module, you of course guess that we can do better. And we will look at that. A first way is to still keep the fairly basic sorting algorithm and do a general purpose sorting algorithm, but one that's geared for strings. So it's general purpose in the sense that you can sort any list of strings, but it's special purpose in that it is strings that we're sorting. We haven't talked about that in Unit 3 because I felt that unit was long enough. In Unit 3, everything was about some abstract object. You're sorting things and you don't know anything more about those, apart from the little detour on integer sorting. But if we sort strings with the usual lexicographic order, there are a few tricks we can play to speed things up. And so one such trick is what's used in this algorithm. Fat pivot radix quicksort. It's at least I like to call it because it's a bit more graphic. It's a quicksort algorithm. I'll comment on the second part in a moment. The fat pivot part just means if you partition with quicksort, remember you pick a pivot element and then there were two options. An element could be smaller than the pivot or larger than the pivot. Now actually there's a third option, right? It could be equal to the pivot. In Unit 3, we kind of treated that case as don't care. You can put it left or right. I don't really obsess about that. And we assume that the keys are distinct most of the time. Now, if you expect to see many equal elements, it is actually smarter to say we do a threefold partition. The things that are strictly smaller than the pivot go left, strictly larger than pivot go right, and in the middle we collect all the equals, all the elements that are equal to the pivot. And that gives you a fat partition, a fat pivot segment in the middle that you can exclude from recursive calls, hence the name. For sorting strings, we'll combine that idea with another little trick, which is we only compare the first character of the strings in each step. But we remember which character we're looking at. I'll just show you this on an example. I think that's the quickest way to grasp the idea. So here's a collection of strings. As I said, these are not suffixes of some text. That's just some strings. And I highlighted the very first character of each. In the first partitioning round, we pick our pivot element. And for the partitioning, you only look at the first character. Ignore everything that comes after that. So we partition around S. So there's B, T, etc. Those go before S, after S, and there's many occurrences of S itself. So if you do that, you find there's only two strings in this list that are starting with something smaller than S, and two that are starting with something larger, and the rest is actually starting with S. So we have three recursive calls, because these are equal to the pivot according to the first character, but not everything. And we have two recursive calls here. Now the difference for this middle recursive call is we know that they start with the same character. So why would you want to compare that over and over again? It's not useful. Instead, you remember that you're now looking at the character at index 1 instead of 0. Otherwise, the recursion is as in quicksort. So again, you have this little subproblem. You pick your pivot, and you partition according to this pivot into the three classes, but one is empty in this case. And once you have singleton classes, you can stop. You don't need to recurse further. For this one, you again pick a pivot. The second character of this one is H. So now the partition is everything that has a character smaller than h, everything that has a character equal h at position 1, and everything has a character bigger than h. Okay? And again, for these middle ones, we know they all start with s and h. No need to compare that over and over again. For the last part, we have a recursive call, and here you see some potential for improvement maybe. We partition, and we find both are in this fat pivot partition. They both have the same second character. And of course, you see that the strings are entirely the same in this case, but the algorithm is blind to that. That's the second round. And we do, these ones don't need further recursions. They're already singleton elements. Same for this. This one we partition further. We pick a pivot. We look at the next character to look at. And that's the second character in this position still. And now, again, everything has the same character. So they all stay in this middle partition. But we remember that they all start with SE, so that we don't compare this over again. In this one, we do have some partitions. There's the ones that are smaller and the one that has an E at the third position. Sorry, I told you garbage. So there's 3 that have an E at this position and 1 that's bigger. Right. So you have to look at this to get the partition here. It can be confusing. In the last example, you pick this as pivot, and again, so you compare the H, and it's the same in both. So you have another round of this. Everyone stays in the middle partition. Okay, by now I hope you get the game. So we pick a pivot, partition according to this character gives you 3 that are smaller and 2 that are equal, where we advance to the next character. Same happens here. If we run out of a string, we fill it up with this end of string marker, which is smaller than anything else. That's the same as we always did. So these 2 end up being equal to the pivot. That's these 2. And shells is bigger. And for this, in the last round, we finally found that the 2 strings are really equal. Maybe we need another round with comparing the $2. I left that out here. I think it's not quite true. One more round here. And here we reach the end. And here. And for this one, you would have to go all the way to the end of the strings. Seems a bit wasteful, but that's how the algorithm discovers that the strings are equal. If you want to read this in more detail, including code, etc., that's discussed in the book. Question?
I was thinking about whether we can use this method to sort instead of some string, but some integers, but we separate integers into different bytes, like 10, like
the digits.
Like
yep.
So that work?
Yeah. So the question was, can we use this method also to sort integers if we just effectively treat an integer as a string, right? If it's written in decimal, or pick your favorite radix. Definitely, you can absolutely do that. It's not such a bad method for that as well. You have to play a bit around with what radix you pick. How well would it work? If you pick to match up something like what we discussed at the time, counting sort or things like that, you would have to pick a really big radix. What you could also think of is replacing this partitioning round with 1 round of counting sort. Then in a way, we're doing 1 round of counting sort, but split over several stages. So the partitioning according to the first character or first digit is partly done here, but then here's complete, but here we split it over the next round again. So we have to combine this and this down here to get the full distribution over just the first character. So quicksort here needs several stages. Counting sort could do it in one. I mean, the short answer is yes, you can use that method for sorting strings. And working out exactly how well it is, or how well it does for that, depends a bit how you choose the radix, etc. But yeah, it works fine. It's not too hard to code and doesn't use this humongous extra space that counting sort used, at least the way we presented it. If you code this up, you have, apart from the two parameters of quicksort for what's the left and right endpoint of the current segment you're sorting, you have a third parameter, which is the position in the string that you're comparing next. And you can only really make use of that if you use the fat pivot partitioning, where you produce the third partition. If you think about the method, by remembering where prefixes were equal, you will never compare two characters that are part of an equal prefix equal between two strings twice. Because as soon as you detect that they are equal, you exclude them for the next partitioning round. And so in a way, the costs for sorting this is a combination of two things. It's, on one hand, it's the sum of all the common prefixes. So that would be the cost to insert all these strings into a trie. And you can show that that's basically the best you can do. You have to detect all the common prefixes. And the second term is a cost that comes from the quicksort style recursion, because you're not using counting sort in the partitioning stage. And you can prove things like this statement, which is explained in a bit more detail in the book. If your strings come from a random source, so you have random strings where each character is just randomly chosen and they're all independent, etc., then you can show that this second part, the quicksort contribution, dominates the rest. And you basically need as many character comparisons as standard quicksort needed comparisons to sort a list. So the fact that you're sometimes comparing these common prefixes vanishes in this case. Now, in a way, that's because for random strings, you don't expect to see long common prefixes. In many applications, and for sure in some suffixes, if we're sorting the suffixes of one text, you will sometimes have these long common prefixes. So there's something to worry about. That's one thing. And for sure, you can't expect this to be better than n log n, because we're still operating on comparisons. Imagine the strings are just one character long, then we don't really use the fact that the characters are integers or anything like that. So we're still in the realm of the comparison-based lower bound. So we're definitely in the n log n regime, and usually a bit worse. So even if you assume some randomness on the strings. Now, in terms of practical applications, I would usually go with this method and give it a try. Unless your string is really pathological, this would do well. But there's two reasons to look further. One is sometimes you can't guarantee you don't run on pathological inputs. And second, it's about the algorithmic possibility. Can you do it in linear time? The answer will be yes. And so it's, at least on the intellectual academic side, I think it's not satisfying to stop at this point. Question? Yep.
Would this be n squared, or where n is the number of characters in the original? Because I feel like you'd have to compare 1 and then 2 and then 3, 4, 5. So
right. So the question was, will this be quadratic for the application on suffix sorting? The answer is not usually. It can be. So the problem will again be strings like this a to the n. If you have, that's what I would call pathological inputs. If you have that, then there's a maximal amount of common prefixes. And the poor sorting algorithm, without knowing that these are suffixes of one text, it has no chance of figuring out the order without finding all the common prefixes. So in a way, it's best possible for that. But still, for this one, it would be quadratic. But for most other texts where you don't have these massive common prefixes, it wouldn't be quadratic. So there's many instances where it works fine. And the benefit from what we've had before, well, okay, I don't want to go over the animation again. I started the section on suffix sorting saying, oh, you could just use any general purpose sorting method. The difference between this and the general purpose sorting method is that this one at least detects the common prefixes only once, whereas the other ones might scan it over and over again, so you might have a log factor difference, something like that.